and actively involved in developing sustainable energy technologies. He pioneered and patented several commercial processes and novel technologies used in the petroleum industry. He has authored more than 300 journal publications, holds more than 30 patents, mentored more than 50 postdoctorate fellows. Chung holds a bachelor's and master's degree in chemical engineering from Queen's University and a PhD in chemical and petroleum engineering from the University of Calgary. He is a professional engineer in Alberta, a fellow of Canadian Academy of Engineering and Engineers Canada, and honorary fellow of Geoscientists in Canada. So please, Dr. Wahed. Thank you.
Well, good morning, everyone. My name is Keng Chung, and thank you, IMP and the organizer, or inviting me here and having me here. Thank you very much. And I'd like to share with you some of our new invention. First of all, I'd like to introduce some about WELL, like who are we in WELL. WELL is a Canadian process license source, and we focus on developing green and safe technology for the petroleum sector. And our company so-called mandate is to try to have an effective resource utilization. Namely, we are focused on maximize the value of the traditional refinery waste or the byproduct. In this case, like C4 itself is a byproduct. And we had office all around the world in Calgary, our head office, and Edmonton, Vancouver, that's in Canada. Beijing, Guangzhou, Dongying, Shandong is in China, and Malta. And maybe if everything goes well, we should have another office in Mexico City. About the agenda of my presentation today, the objective is to provide you with an overview of our Ionikylation technology. And I also like to share with you some data from our commercial operation. So to give you a flavor of what the thing look like when you get into operation. And the presentation will encompass a few items here, the alkylation overview. I think most of the expert in the last, three presentation already say a lot of those details. So I'm not going to go through a lot of those. And then again, to the heart of the ionikylation process itself. And then I will share with you the commercial cases. And then I will wrap up with some new thing that we are working on. And just to give you an overview, as you kind of follow the news, the alkylate demand is going to be going up for quite a few years to come. Okay, and one of the key requirement is because now we have high performance car, and they require higher octane type of fuel for the car. So, and they are getting bigger and bigger. And when they come down to produce an alkylate, I think in the last few speakers already mentioned. So the question is, what are the best we have today, right? So obviously the existing one is either you do the HF or you do the sulfuric acid. And we know what are the so-called like the downside of those kind of technology. And I believe as of today, the only commercial process that we have is our ionikylation process. And this is safe and environmental friendly. So I'd like to kind of like flash for some of you that are not aware about what's happening in the last 10 years or so. You know, like the alkylation process have been around for 75 years. And obviously this process have been, you know, like as the speaker before me mentioned, they put in a lot of the safety type of precautionary check to make sure that it runs safely. And I think, you know, that seems to do the job for quite a while. But I think everybody agree that the fact is refinery are getting older and older. You know, for instance, like our industry is 100 years old and alkylation is 75 to 50 years old type of technology. Sure enough, this type of wear and tear thing play a key role in there. And I think some of the reality that we are facing in the oil industry is because the price of the oil up and down. So there to be some time, the refinery are forced to defer some of the maintenance service. And sometimes this thing is going to cost you something in the long run. And these are some of the picture I can show you. Like these are the near miss. You know, it just basically had an explosion that nobody get hurt. Okay. But some of them are a little bit more extreme, right? On the left-hand side is the one that happening in Pennsylvania in 2019, and that plant is pretty much like shut down and bankrupt right now in Pennsylvania. And on that is the HF unit. This is the HF, and this is the one in 2022, which is very close, like 2 years ago in South Korea. This one is a sulfuric acid. It's about 10 years old. One person get killed and few people get hurt. Okay, and this kind of thing that, you know, I think it get the headline, and I think a lot of people catch attention because in today's society, I don't think people can kind of like take the safety like take it for granted now. It's actually the main issue. And when they come down to safety, or if you talk about some hazardous type of situation, as I say, you know, you can put all the effort in there to make sure that these things don't happen. But if the process itself has some intrinsic style of so-called a hazardous component in there, it's a matter of time that it will happen. Because that's what I think even our last speaker have been mentioning, is a lot of the human issue that come into play. And this is what I think, you know, in our process, the good thing is like, I can show you some pictures later, we don't have any of the concern at all. And the only thing that as a refiner you had to be aware of is just to make sure you deal with all the hydrocarbon. I think this is pretty much the main part of our business is hydrocarbon processing. So I skip this, right? And get down to the alkylation, our process now. So in our process, when you look at it, it's very simple, right? Basically, you had four components. Oh, sorry. You have four components. The first one is the feed pre-treatment, the reaction section, and then you have the product separation, and then this is what we call the catalytic regeneration system. So when we look at this kind of this process, very similar to what we have in the HF, right? You have the feed pre-treatment, and then reaction, and then you have the product separation, and the catalytic regeneration. So for like, in the case of, let's say, Penmac or some of the existing refiner, if they like to do the revamp or retrofit, the only thing they need is just replace the reactor system and the catalytic regeneration. And you can keep the rest the way it is, okay? So that's the heart of our process. And just to highlight a few things, right? As I mentioned, the catalyst that we are using is intrinsically safe. It's just like any hydrotreating catalyst. You can play around with your hand, you know, it's not a big deal, right? But we don't recommend, but that's what it is, right? And the catalyst is highly active, has high selectivity, and you don't have to worry about any acid runaway type of condition in the operation. Another one is very obvious, no corrosion issue, and you can use the entire process using the carbon steel and for the construction. And the integrated catalyst system is kind of everything is all by itself. And some of the advantages in terms of our process compared to the existing one, obviously the safety. Safety is the one that come out right away, right? Because we don't have a corrosion issue. The stuff that we are dealing with is not a hazardous material. And then when you look at the so-called the composite ionic liquid that we're dealing with, of course, a lot of people in this audience, you are aware about the ionic liquid, right? So these are some of the characteristics of ionic liquid. Ionic liquid itself is a liquid salt, okay? And it's highly, like you can manipulate the component, so you can play around the composition, and you can get different type of so-called the catalytic activity, meaning the function of this ionic liquid. You can play with the composition. And I had to just caution you, most of the ionic liquid is corrosive. Okay, most of the ionic liquid itself is corrosive. So what is the difference between our so-called catalyst and the ionic liquid? Ours is a composite ionic liquid. In other words, we put some extra ingredient in there to make it non-corrosive. Okay, I will give you a little bit more detail in terms of how we come up with this thing. So as I mentioned, we are non-corrosive, and I guess these are some of the functions that very similar to ionic liquid, like have low vapor pressure, the density is very high, right? The viscosity, not bad, and now it will decompose. If you heat it out, it will decompose at 200 degrees C, and the freezing point is about 3.8 C. As you can see in the middle here, this is what our composite ionic liquid look like, right? So in other words, when I start to see this, I'm kind of like, oh, there is something else that we can use. The reason is like when we start to do this work, and when they start to mention about like this is a corrosive material, me being working in the refinery for 20 years, it's like no. And the guy say, well, it's not so corrosive. My first impression is corrosive, less corrosive is still corrosive. So I say, no. You have to give me something non-corrosive. So this is, it comes to like, what we have today, right? You can see from here, right? I mean, like even you have this ionic liquid drop onto your skin, you just take the dry cloth, just clean it, and it's done, okay? And you can see on the right-hand side here, right? This is the composite ionic liquid itself, and this is the alkylate. So the good thing about this is like, if you do the process, the separation side of the product, because this is 1.4 gram per cc, and this is about 0.69. So right away, when you actually put this so-called the product come to the back end, it separate right away. It's very easy to separate the alkylate from the catalyst. So this is another part that we talk about later on, is like how you actually make the chemistry and you turn that into a process, because you have to meet all these criteria from the scale up point of view. Then the next one, like you ask ourselves now, okay, like this is very quick snapshot first. When we talk about, when we talk about like our catalyst have the good what they call yield and selectivity. So how different it is when you compare, because a lot of people do ionic liquid. How different it is compared to the conventional ionic liquid as what we have on the composite ionic liquid. First of all, when you look at the ionic liquid and the what we have, both of them give very good yield for the alkylate, okay? But as you can see on the ionic liquid itself, this is very non-selective. It's everywhere. But in the case of ours composite ionic liquid, it tends to be very selective. You see, like the C8, we get 96. The rest are very low. In other words, you put C4, you get C8. You put C7, you put C3, you get C7. You put C5, you get C9. That's what it is. So they don't have a lot of so-called the side reaction or the secondary reaction. Very selective. Then the next one we talk about, that's the reality. How corrosive it is. Is there any problem with so-called metallurgy? So this is one of the first installation we have. And this plant was running continue for three and a half years. And because it's a new plant, and at that time, the government had the regulation is this is brand new. Like there's nothing before that, right? So it's a brand new like process. So they insist that we should shut down to do an inspection, and we did. So we shut it down to do the inspection to make sure that everything according to what the requirement. And the conclusion is there's no noticeable corrosion, so-called like phenomenon. So it's safe. So it's also safe. It's just like there's no corrosion issue. And after that, he put it back again and it's done. Then the next thing, I guess, you get down to like how you deal with the so-called the spent catalyst. So if you can see from here, when you actually take the spent catalyst out from the reactor system, they look like paste, like wet paste. And then you just basically just dry it. Eventually, it become like how to say this, like soy, because ionic liquid is a liquid salt. So eventually, when they dry it out, it's like salt, like sand. So it's very easy. Like you can dispose of it either by just go to the landfill or go to the cement factory. Can make cement. So it's not an issue in terms of how you deal with the spent catalyst. So now I want to just touch base now to talk about our journey. How we come out with this so-called composite ionic liquid and how we come to this ionikylation process. So I want to tell you a story, because if you go to the website and look at what our group have been doing from day one, we don't do anything like. We only do one thing, byproduct. What are the byproduct? Bitumen, petroleum resid, the bottom of the barrel. Meaning, the challenge of the refinery until today is that there's no better way to deal with the bottom of the barrel, and you had to use some kind of like waste treatment type of process, like coking, gasification. These are waste treatment. And we thought about something is like, is there any better way we can do this? And some of you, if you are in the mid-90s, ionic liquid is like a wonder drug, right? For instance, when you look at the literature, it's a green chemistry. I think back in the 90s, we already started to talk about green thing. It's not today, okay? We talk about green thing in the 90s. And when you look at the literature, ionic liquid is a wonder drug. You can basically do anything that you can think of. So we look at it, it's like, man, that is really cool. We should try something, okay? So you think about it, right? For some of you aware about, like at least familiar with the refining process, if you want to do the cooking process to cook the bottom of the barrel, that process is running about 500 degrees C. And you get all the different type of animal coming out, okay? Not a very good product. And then you have to do a lot of hydro treatment. That's another expense. So we are thinking is like, can we actually use ionic liquid to do cracking, to do the cracking of the petroleum resid, right? Because you can run at the room temperature. It's like you save a lot of energy, save a lot of cost, right? Well, we tried 2.5 years. Nothing happened. Nothing happened. So now we're in trouble, because we spent 2.5 years with all this time and money. Now we had to basically write a report now, what to do with this investment, right? So I start to ask my guys, say, look, please tell me how you spend your time in the last 2.5 years. And we went through though. So this is what we are going through, okay? We start to do, like obviously, like when we start to do the bitumen, we also do something like what the literature suggests, like do alkylation, right? To do C4 instead of bottom of the barrel. So we just like do this kind of like cross-check. So now you see what we are going through? Like that was like 23 years ago. We start with very standard ionic liquid, okay? And then we start to make it more active, right? So now what do? You play around with the different composition. Well, it's not high enough, or we put some acid in there, right? We put some hydrochloric acid in there. I think, if I'm not mistaken, the UOP process, the ionic liquid system, I think this is what they have right now. They still basically activate, they use some kind of acid to activate the ionic liquid, right? So obviously, when it comes down to here, obviously, like it seems to be you get a good yield, but it's very corrosive. So I say no. As I mentioned to you, I'm in the refining floor. I can't accept that, right? Because it's too much trouble to deal with all these things. Then the next thing is like, okay, so I say, what else do you do? She say, you know what? We start to play with, add some other thing in there. So we put some transition metal. In this case, we put some copper chloride. So this is where we talk about composite ionic liquid, right? You put a little bit different addition material into it, right? And then we start to play with this thing, and right, sure enough, it seems to be we don't have any corrosive type of behavior now, but the product coming out is like a suspension. Like for instance, like this is why I think we have to understand what is the chemistry and what is the process, right? You may have a good chemistry, beautiful chemistry, but if you want to turn that into the process, you may have to make sure that the product that you make, you can actually separate them out. It's not like emulsion that you can't even separate out. So this is where we are getting into like, okay, what else we need to do now? So after they play with a few things, so eventually we come up with what we know today. We basically had a composite ionic liquid type of material, and it's not hazardous, right? And you still get a good yield, and then you get good selectivity, and the last one is good separation. So now we say, boom, the light came out. So this is where we start again. Oh, excuse me. Excuse me. Can you? Oh, okay. So for some of you have some dealing with the ionic liquid, you probably know what I'm trying to say here. Is like, you can basically just it's a very simple thing in a way. It's a salt, right? So you basically have the alumina type of material, and you have some chloride, and then you manipulate them depending on what the composition look like, and you basically can like change the so-called like the function, the acidity function. So obviously, like when you play with those things, you get into manipulate the Bronson acid and the Lewis acid type of the split. So this is pretty much the heart of ionic liquid, like how they can do they can get the high acid function for your reaction. And as I think yesterday, I think I did mention about what's the big difference between like HF and the sulfuric acid, as you can see from here, right? And this is like this is what the HF is sitting here in terms of the solubility. In other words, when you basically have this light hydrocarbon and you put it in HF, and it's very soluble. And it turned out the ionic liquid or composite ionic liquid, they are also very, like it's a good solubility. As compared to the sulfuric acid system, look at it's almost like a magnitude. So this is what yesterday one of the speakers was saying. You know what? If you decided on the HF, you can't really change it to a sulfuric acid because they're two different systems. Now you know why, right? Because intrinsically, they're two different animals, and you cannot change them, right? So when you decided. So I want to share with you another thing about how we do the development in terms of the process. So as I mentioned, we are not alkylation guy, okay? We started learning the trade 23 years ago. So the question is like, okay, it's just like when you start to learn something, you like to basically kind of say, is there something that I can follow? At least you can follow like a system. So this is where we come up with the strategy. At that time, we look at ourselves and we say, you know what? As I said yesterday, HF from the chemistry point of view is a very good so-called reaction system, okay? Except it's corrosive. So the next thing we ask ourselves is like, okay, except for that now that we are already done with it, because we get rid of the corrosivity, now we have asked ourselves now, say, and dangerous, right? We say, okay, look at the property, look at the composite ionic liquid and the HF, very similar, right? You had like good solubility for the hydrocarbon. So this is why, like as I showed you the slide earlier about our process, it's very similar to the HF, except the two things, the reactor system and the catalytic regeneration system. So for people like who, let's say, already run the HF system, if you ask them to put some new process, entire thing new, that's a lot of learning curve. So we are thinking like the easier and the best is like we can kind of like, like piggyback on what we already have. And this is where our platform are based on HF, but we don't do HF. So as I mentioned to you about our advantage on this one is this. I think the key is like, if you visit our plant today, you don't see any water curtain. The water curtain is the one that, you put it like a sprinkler system. In case there's any leak, you can spray. In our process, we don't have any of those because we don't need those. It's not an issue anymore. And sometimes when you drive through the plant, you don't even know there is a alkylation system there. So I guess from the engineering and from the design, it's like, or even operations, right? We don't have any problem, like, or safety concern at all, and it can be contained easily. Even you come to the worst case scenario, if you have any leak or whatever, it can be easily contained. That's not an issue. You put some water in there, it's done. Like when you put the water into the composite ionic liquid, it breaks everything. It decomposes everything. Oh, sorry. And I mentioned earlier, right? The good thing about this, it has high solubility for the isobutane. So in other words, when you look at the reactor system, this is where we kind of learning from the HF system. What kind of like mixing system do you need? So it's very similar, even though we have some upgrade version of the reactor system, but it's pretty much the same. The science is still the same. The science is still the same. And then the next one is like we had a very good, as I mentioned, like good product separation system, like because of the density different. So that is to make the entire process very easy to operate. So as I say, when we start to play with this ionic liquid, and as you can see from here, right? Like when you actually do this fast atom bombardment mass spec, right? So you can see the difference between the conventional ionic liquid and the one that we have. You see in here, we actually have a few peaks, right? And then obviously, like depending on what the composition is, like you can just kind of manipulate the composition here, but this extra one is the one that we have the copper in there. So you can see very clearly on the MMR, right? This is the big difference. This is the obvious difference between the so-called like the conventional ionic liquid and the composite ionic liquid. You have another peak coming out on the side here. So in other words, like when we talk about this, it's not magic, it's a science, right? Whatever we think that we have, we had to prove that we have. And then this is where we start our journey, like that is 1998. Then after we done all the so-called like benchtop lab work, then we start to do this so-called like proof of concept pilot in the lab, like in the small scale. Like this is, I think this one is 20 barrel a year. It's a small operation. Just a proof of concept. And these are the data from the so-called like proof of concept, right? So as you can see from here, right? Like we the mix going, the so-called the feed going in and the product coming out, right? And let me see now, do I get this thing like, oh no, sorry. These data are coming from I think 2004, when PetroChina basically allowed us to have a retrofit to do a demonstration trial. They have a so-called old structural process, and I think it's about 15 years old, and it kind of has some leaking, and kind of say, well, there's a process sitting there, you can play with it. So we are fortunate that actually have PetroChina that give us this so-called like a small commercial plant to do a commercial trial. So in 2005, we actually do a commercial trial, and these are the commercial data that I have here. So the before and after, as you can see very clearly, like you actually have to see In other words, when we start to do the small one, we had to basically say, can we demonstrate on the big one? Okay, so how are we going to demonstrate a big one? There's somebody willing to let us trial on their system. So this is what we get. And then on the run, like in their old system, they get 95. When they put ours in there, they get about 99. So it's obvious, right? We got something. And by the year 2013, then we start to have standalone, all by itself. So this is one of the small one. We have the greenfield installation that is 11 years old, already in 2013. And this is the one that is a small unit. It's actually have a small petrochemical plant. They built this. And then the next one, 2018, we had the China one coming out. And then we have another China. And then we had the Sinopec. And then we have Sinopec again. And then Sinopec. And then another one is China. So the reason I show you this is like yesterday, one of the speakers was saying, you had to do all these consideration, you had to do all this economy type of evaluation. One thing he didn't say is like, no one wants to be the first. So we have to show people that we actually have a lot, like, at least we have 7. Okay. So now even let's say, PenMec, it will be number 10 because we have 2 more coming out. Yeah. So this is just show you something like, it is commercial. Now I want to give you the case studies, right? Because like when you get into this, people want to ask now, how is this perform? Okay. And so this is the real thing. So this is one of the first Sinopec plant up running. So on the feed composition, as you can see from here, this is what I want to show you. What is design and what is actually like operate, right? Like on the design case, like for instance, when we start to do this engineering, we have to say, hey, what is your feed composition look like? Then we can do some prediction or we can do some design. But in reality, as you can see from this table, is I won't say it's very different, but it's not the same, right? Obviously, it's not. It's similar, but not the same, right? Look at some number here, right? NC4, IC4, not quite the same, right? And then when you look at in terms of the difference between the different kind of component that we have, as you can see from here, like it going from like 0.5 or something to about 50%, up and down, up and down. That's the reality. Right? So in other words, it's not in the lab, you do good model compound, you can repeat it all the time, but in reality, in the plant, no, right? You grab a number and then the next day might be different. So that's the reality. And then you also notice something is this, in the plant, because the C4 is a byproduct of the FCC or the MTBE. So a lot of the C4 is all depending on how you run your FCC. You may change the feedstock. You may change the operating conditions. So this is all the whatever animal that you get. Okay, what you get is what you get. So that's the reality, right? So I like to share with you some of the right? So you can see though. So obviously, like in alkylation reaction, the only thing that is of interest to us is the IC4 and the butene, right? The rest are just tag along. Yeah. And then the next, by the way, in our case, the NC4 is just go for a ride. They don't do anything. The NC4, they just go for a ride. They don't do anything. Even the NC3, they just go for a ride. But on the front end, we tend to take those things out as much as you can, and we leave the NC4 because when you have NC4 and IC4, it's very difficult to separate. And we leave it there because some of the refiner, they may want to use the NC4 to blend to get their vapor pressure up or down, depending on the season. Like summer, you basically have the lower vapor pressures. And winter, you like to have a higher vapor pressure. So this is how they're designed to meet their purpose. And in terms of like when you look at the material balance, right, you can see the overall one, like the design we designed for the 37, the commercial is about 40, right? But when you look at some of the what we call like the non-reactive component, this one. So already, as I say, they go for a ride. And if you can see from here, like even though the design may be even higher, but the commercial one is actually slightly lower. And then the next one, you look at what the overall material balance look like. Okay, so as I mentioned earlier about this part here, let's see, right? And then when you look at the product now, right? You can see like the design one, you actually design actually higher, but the commercial one is actually lower. And as I mentioned earlier, the key difference is because of the IC4 and the butane that you have, right? So at the NC4, the one that go for the non-reactive is pretty much is the same. And then the end of the day, when you look at it, because of the commercial one, you tend to have some light material, so they flare some of the thing off. And the end, you get, here, you get 45 and you have 39. That's about what the ballpark might look like. And in terms of the spec, for instance, every refinery, they have the spec for their alkylate. And what we have here is pretty much whatever we have in our commercial system, it pretty much meet or better than what our design parameter look like. So that's not the issue at all for our product. And another one I like to kind of like mention about this is like, when you look at our process flow diagram, is it actually even simpler than what we have for the HF or the H2SO4, because the product we make, first of all, it had a very low boiling point. Like they don't, especially when you get down to, let's say, the high end, and in our case, it all within the gasoline boiling point. We don't need to have another extra type of separation to cut off the heavy end, because we don't make those heavy material. We don't make very light material. So this is some of the key parameter that we have. And as I mentioned earlier, our process is extremely selective. So this is the commercial product, right? As you can see from here, like the only thing you have is like C4 to C8, boom, C4 to C8, that's it. And then obviously, there are some small amount of the secondary type of reaction. They make some of those, but low, very low amount of this. But they are still within the product range of the alkylate. So what I would like to highlight earlier is when people talk about yield, yeah, they say like you have high yield. Well, we also have high yield. The question is how selective you are. That's the key. Yeah. Then when you talk about I think yesterday there's an audience asked about how much does it cost, right? So this is what I want to share with you. Like here, this is the cost. Like the design, this is pretty much for the 300,000 ton a year operation. I think it come down to about 7,000 barrel a day. Right? So this is not it's a medium size, it's not a very big one. I think Penmac has something bigger than this. But nevertheless, as you can see from here, in our system, what you do is when everything is new, you charge it with the composite ionic liquid catalyst once. Okay, and then after that, you basically just add the so-called the key ingredient, right? Meaning when you deplete the so-called composite ionic liquid, you had to make up those components. And in our system, we kind of make use of the process to actually start to make the composite ionic liquid. So we just basically just put the so-called the component of the composite ionic liquid, put it in the system, and then the catalyst rendering system will start to react and make catalyst itself. So as you can see, we don't put any, like yesterday there was a question too, do we put any hydrochloric acid? Answer is no, we don't put any hydrochloric acid in there. So in the design case, this is what we based on the previous case, right? But in reality, when you actually run this Jiujiang, the first Sinopec unit, amount of the catalytic consumption is much less. So I want you to hold on to this because we are actually make some improvement on this, and later on you can see what are the so-called enhancement that we are doing. And obviously this come down to the cost, right? Because when you run the process, the question is how much is the cost of the catalytic. So now you just based on this material, you know what the cost look like. And for all the practical purposes now, our system, because there's no new HF being built in the last 10 to 15 years, the new one are all so-called the sulfuric acid. So we kind of do the cost comparison against the sulfuric acid. And I can say this, when we have these 7 plant running, our operating cost is neck and neck, is almost the same as the sulfuric acid. Okay, because obviously sulfuric acid is very cheap, but this one is like a chemical. You have to make them. However, today, because of the environmental requirement, they require, like for instance, like they put the limit on in terms of the sulfuric, the SOx that you can release. Because when you actually do like the post treatment of the spent sulfuric acid, there are some like sulfur emission coming out. So they put a cap on those things. And because of this new regulation, at least in China, the cost of running a sulfuric acid become even higher than what our system now, because of environmental cost. And these are some of the, like we mentioned about, like when you run the process, you need to have the type of pre-treatment to prepare your feed for the alkylation reaction. And this is pretty much what we have in the HF. Is very similar, right? So these are the requirements that we need. And so you may ask the question now, if I basically kind of like, have some criteria or some of the number higher than what you asked for, what would happen? Well, nothing will happen except you use more catalysts. So for all the 7 units that we know today now, we never suffer from the quality. In other words, whatever we design, what the RON number look like, the 96 plus, we always meet the 96 plus. Even though in some cases or some incident, you basically have the offset, you basically have some high in certain criteria. The only thing you end up paying for is you need more catalysts. You just kill the catalyst. That's all. So I kind of try to wrap up this part, like, so all this year now for almost like, 20 some year and that more than 10 years of commercial experience now. And what we learn is like we can get a high quality alkylate, right? Despite you get different type of feed going in there. And today we can actually just by looking at your feed, we can tell you what the product might look like because our reaction is so selective. And most of the prediction, I know when you look at all this now, right? So if you're looking at some of the operation like we are looking at right now, it's all like focus on all the hydrocarbon. It's nothing to do with this so-called like the catalyst that we are dealing with. In the plant, they basically just focus on like how you deal with all the. So for me, this is not our problem, basically, from the licensors, right? Because this is pretty much like the refinery had to deal with the hydrocarbon with or without having our process, right? But that's part of what they are doing, right? And then as I mentioned earlier, right? The reason you basically decide to actually take out the butane that you're not reactive is it all depending on what the commercial plant want to do with it. So again, it's not really the heart of our process. It's actually more like the engineering, what the refinery want to do. But this is something like. No, we can tell the refinery, if you have something that in mind, you can do it this, you can do that. So now we have all these database that we can share with the user now. And again, the pre-treatment is the key, right? Because if you don't have a good pre-treatment, then you pay a little bit more for the catalyst. That's all. But you don't suffer anything except pay more for the catalyst. Yeah. So some takeaway, right? The bottom line, Ionikylation system is a safe and is a sustainable clean fuel production, right? It eliminate all the reliance on the toxic and the dangerous acid that we are using today, right? Non-corrosive type of catalyst and high activity and high selectivity toward the manufacturing of the valuable product, right? All equipment can be manufactured with this carbon steel. So in other words, if you basically decided on our system, like typically about 1.5 to 2 years, you can have the operation because all carbon steel. But in some other system that we know of, like the HF or the sulfuric acid system, when you put in the order, it takes much longer because you need to have a special alloy to make those reactor, right? And today, as I kind of summarize this, we have 7 commercial units, including 1 re-ram on the HF, and and nearly, like as I mentioned, we have more than 10 year of operation experience now. So the next one I want to tell you what's next. Being new, this is what I told some of our users today. Being new, you expect to have a lot of add-on, some new improvement coming, right? When you basically deal with old stuff, that's it. So as I mentioned earlier, we are doing this the second generation composite ionic liquid formulation now. So what we are doing, one of our operator now, they are using this. So the idea is instead of 82, you can bump up to 90 higher. So in overall, you can increase the run by 2 number. In other words, whatever our process design right now, with the new catalyst that come right now, you can actually instead of design a 96, we can design a 98 run. That's one. The next one, as I mentioned earlier yesterday, we are trying to replace this one now. So in other words, we know exactly what causing the catalyst to deactivate. So now we have the new catalyst regeneration system now. So to replace what we have in terms of just doping the new stuff. So then the question is like, what do you get? So as I showed you earlier, instead of just paying for this like 162 kilogram an hour of this so-called composite ionic material, we don't even do this anymore. So what we are going to do is we're going to have this, and then we can basically reduce the amount of the catalyst. We're just going to put the makeup. So it will be kind of like going down from 160 to 40. So you can reduce the operating cost by that much. So this is upcoming. So our pilot plant are running, and we should have the data by the end of the year. And something I want to kind of like share with PenMec, as you can see earlier, we talked about that there's going to be increased demand for the alkylate. And when you look at it, we look at the big picture, right? As you can see from here, the oil demand is not coming down, right? Right now we are somewhere here. And by the year, let's say 2045, at least 20 more years, that oil demand is still high up there. So with that, we expect to have, the X barrel of the gasoline need to be produced. So this is why I think there's a window opportunity for Mexico, for PenMec. Because North American refinery, they are not adding any more refining related type of equipment or capacity, and they are not doing any. But they need a lot of alkylate because they need a lot of high octane gasoline. This is why I said here is like, PenMec have the market niche to increase the alkylate production to fuel the North American market for the next 20 years. Okay. So some of the forecasts were saying that, in the second half of this year, the U.S. high octane gasoline price will go up by $1 per gallon. So just to give you some number about what people are thinking of. Then the next one I think is very, something to think about is like when you start to build a new process, you have to start thinking now, 5 years from now, 10 years from now, what can happen, right? So we offer something like this. We say, our process have high process flexibility. For instance, in the base case scenario, right? In the base case, we are saying something like, okay, we can basically do a base design as 96 run. However, if there's a high demand for high octane, type of gasoline, you want to make more alkylate, you can basically put a compressor in there. So, okay, why you put a compressor? The function of the compressor is to cool down the IC4 coming back to the reactor. So when you bring the temperature down, you increase the selectivity. You get more higher RON. So you can get to 98 RON. Okay, 96, put a compressor, you get 98. So another scenario you think about, say, oh, what happened after 20 years? Even Mexico, gasoline demand may even drop. It's a whole world may drop. Well, you don't need to worry. Why? You've just put a product fractionator and the alkylate. You don't just talk about alkylate now. You also make chemical. In other words, as I mentioned earlier, because the process is so selective, you put C3, you get C7. Okay, you get C7. You put C4, you get C8. You put C5, you get C9. So what we are proposing is like, even though your market demand may be reducing for the gasoline alkylate, maybe you can just focus on just selling the C8 for your gasoline blend, and then you sell C7 and C9 as chemical. Like for instance, a lot of cosmetic the lady are using, a lot of them are C7 or C8 type of material. So this is something that you can think about, right? Because we're getting more into, even for instance, the bigger picture is like, don't burn them, okay? Because if you burn everything, then it's like more CO2, right? So in other words, if you put all the alkylate into gasoline pool, you're going to burn them. So what we are proposing is like, maybe the market demand, maybe is a pressure on CO2 emission. You may want to do this because you don't make a lot of CO2 anymore, right? When you actually do C7 or C9 type of solvent, you make into consumer product. Okay, yeah, I'm done. Oh, I'm done. Yeah, I'm done. So now you see, like the bottom line, we had to make PenMac very happy. Thank you very much.
Thank you, Keng.
Yeah.
Thank you. So now there's some time for questions. Please, someone have a question? Who can first? Dr. Natalia, please. Please.
Yeah. Oh, hey, you want to take picture of me?
Yeah. Thank you very much, Dr. Keng. I have one question. What is the mass relationship between catalyzed and feed mixture? What is mass relationship?
Oh, that's easy. Like for instance, when you actually, as I mentioned earlier, I think the yesterday's speaker also said something too. In this type of alkylation reaction, the key is the butene, right? The butene, right? But then the other part of it, the propylene, butene, and what was it? The C5, the 2-bond C5. These are all the active ingredient, the double bond. And then basically you put in the IC4 to basically react to make those products, right? So right now we just talk about C4. So it's almost like it's 1-to-1. In other words, when you look at our product, we don't have any other so-called, because the IC4 is in excess. IC4 is in excess. So you basically use up all the double bond. Okay. Then the next question is always, when you actually use up all the double bond to do all the reaction, how selective are they? Because like I think yesterday the speaker mentioned already, this is very exothermic reaction. It's very fast, right? So this is why you get into the reactor design. Now, a guy like me are not good in organic chemistry, right? I need to confess, but I'm good in reactor stuff because I'm running a refinery. So this is why we have to thinking how to cool it down fast. So in our reactor system, very fast cooling to cool it down. So we basically kept it. So the end of the result is whatever we go in there, we try to minimize as much as we can all the secondary reaction. So this is why we are so sure now today. Now, you put C3, react with IC4, you get C7. C4, you get C8. C5, you get C9. Done. And it's 100%, 100% react. Yeah.
A bit shorter than the other questions.
Yes,
so
yes.
We have more time for the questions.
Yeah.
Okay. I think there's another question from Professor Dr. Dominguez, please.
Hi. Oh, very good, very good talk.
It's good. It's good. It's working.
Yeah. Very good talk. Thank you. Then, if you accept two questions, first one is how acid is your acid catalyst, and the next one should be what is the proportion of ASO, I mean, acid soluble in oil with respect to the product. Could you please? Yeah.
The first one. It turned out that we don't want it to be very, very high acidity, because so the end of the day it is, right? We want to have very selective, like, product coming out, right? That's why you see, like, like you have C7, C8, C9. If you get too active, right, it just becomes like this. Sometimes you getting out of control. So this is why, I always say something about, yes, we need to have high acidity to do the alkylation reaction, right? But the problem is, HF and like sulfuric acid, they are acid. They are not like, for instance, like, our friend in doing catalyst. They can manipulate the property, right? You can manipulate, they can. But the good thing about this one is you can manipulate, like catalyst, you can manipulate them. So back to your question, we don't want it to be too high. When you're too high, no good, right? You shoot yourself on the foot, right? Yeah. So the next question about, like, you call OS, what we call ASO, right? Yeah. These are trace amount that we cannot kind of like get it go away. It's part of the deal, right? So this is where we start to think about this for the last 10 years now. We decided, we did the small lab test already, I've had a small lab pilot, right? We can easily remove the ASO, just hydrotreat them. So this is what, the heart of the new catalytic regeneration system that we are building right now. Yeah, you do hydrotreat, boom, they become like diesel cut type of material. Yeah.
Thank you. Thank you. Dr. Jaime Sanchez, please.
Yeah, a question. Yeah, what is the cost production using the cost production compared with HF technology? Could you talk about that, please?
Wow, this is why I think yesterday I mentioned about why HF have been around for so long. First of all, the chemistry is easy, right? Second of all, you can get HF from mining, right? Like fluoride from mining. Easy. Obviously, ours is more like the chemical process, right? So the end of the day, yeah, when we actually start to do though, obviously, like it's not the so-called like the showstopper. In other words, the cost is not, ionic liquid, you look at component, right? So one of the key ones, because we are using copper, so it seems to be today, one of the high cost is the copper. So it will fluctuate a little bit depending on the cost of the copper, but it's manageable. Yeah. So this is one of the operating kind of information that we need to share with the user. Yeah. Yeah,
okay.
one more.
Yeah, one.
Yeah, well,
Okay.
I think that for justifying the introduction of this process into the industry, you have to demonstrate that it has economical benefits. The question is related to the question of Jaime. I wonder if you have a specific value of the cost of production of the alkylate compared to other processes using sulfuric acid or fluoridic acid.
Yeah.
This is important independently of the benefits of the environment you have.
Yeah. In our case, that's it. When you buy the catalyst, boom, that's it. This is all operating cost. But in the case of the sulfuric acid, it's not done yet. Because all your sulfuric acid, the spent sulfuric acid, usually people don't do it on site, right? And most of the time, people don't even do that. They just dump it. But you pay for it, right? So this is why I said today, at least in China, it's more expensive when you actually start to pay someone to get rid of your spent sulfuric acid, and one of them go to jail because they pump it into the ground.
Okay.
Yeah.
That's a good question.
So this is, yeah, fair enough. I think, you know, once you basically have this, so like the operator, yeah, we give you all the number, and we also tell you, you just track the copper price up and down, and certain component will go up and down. Yeah. And today, I just one more. We have 2 manufacturing facility in China. Just in case, right? Yeah.
Thank you.
One thing that
Sorry, I think you better discuss after when you have some free time. We are done now, so we have to continue with the program. Well, I want to thank you. I want to thank Dr. Chung for his presentation, and I want to give this acknowledgement and a small present. So
Thank you. Thank you.
thank you. Okay. We will continue at 11:05. I'll take back the one of your colleagues. I will take it back.
Oh, yeah. I know.